Good evening, everyone. My name is Vicente Alvarado, and together with my teammates Josue Alcibar and Douglas Consabay, we are going to present our project titled Autonomous Drone Design and Validation in a Simulated Environment. This project focuses on how drones can be developed and tested in simulation before being applied in a real-world scenarios. As you know, drones are becoming increasingly important in logistic and urban delivery. However, they face big challenges, such as carrying payloads, avoiding obstacles, and navigating safely through complex environments. The problem statement. The main problem we address is how to control a drone to move safely from one point to another point in a complex urban environment. The drone must follow a trajectory with avoiding collisions, which require calculating both positions and orientation in space. In other words, position and quaternions. Without precise control, the drone could crash into buildings, trees, or other obstacles, especially when carrying packages. So, the challenge is to design a system that enables stability navigation, safe path planning, and real-time adaptation to its surroundings. The methodology. To tackle this challenge, we designed a complete simulation framework. We use ROS2 as a middleware to manage communication between the drone and the simulation. We use Gazebo to visualize the drone 3D flight and test its kinematics and dynamics. We also integrated cool ground control for mission planning and monitoring, and tools like RVs can be used for visualization of sensor data. The drone model was the X500 equipped with a peaceful flight control.
So we can use an additional vector with P, Q, and R defined as the derivative of the roll, pitch, and yaw angles to obtain the angular velocity vector. Then, because we use for motor for the quadcopter, we will have four different types of angular velocity, and all of them we produce thrust and drag torques, where Kf is property thrust constant and Kn is the drag constant. Next slide. For the control and the input rates, we can define the four motors as next. First, the motor 1 in the front left, the motor 2 in the front right, the motor 3 in the right, the motor 4 in the right left. Later to define these motors, we can define two different types of motions, like elevation, so can be to up and down the drone with the right position, with the correct position or positive position of all the motors, the roll motion with the 2 and 3 right position, the pitch motion with 1 and 2 positive position, and yaw with 1 and 3 positive position. Next. Oh, okay. And talking for the dynamic model, we use the rotational matrix calculated before to compute the translational dynamics. The translational dynamics depends on the mass of the robot and the derivative of the velocity. Then rotational dynamics that depends on the second polar moment of the second polar moment inertial of the robot and the derivative of the angular velocity. All depends on the Euler angles. Then we can compute a final vector with the derivatives of the Euler angles, roll, pitch, and yaw. All of these matrix can be used to simulate in ROS2 and Gazebo, and finally to put the code in the control Big Hawk.
The control is implementation of the simulation use a dynamic control, in this case, on nonlinear UAV model. In this case, this is based to the difference equation to explain it in the part of the equations of the dynamic and cinematic movement of the drone. Additional to the difference adapts to winds and payload change that is modified with the different inertial of the different components. Consider this, the PX4 firmware adapts the drone to a specific model to flight when it stabilizes. Additionally, this model uses the IEMU that calculates the different positions, speeds, acceleration of the drone in the different translations and position coordinates. What is the result of this project? Well, the result of this project is different note that communicate the drone with MacPros. This is a communication to the drone with MacLink between to operate with telemetry. Additional to a node that modify the position of the drone between of the translation points and a quaternion that determine the orientation. In this case, you can see a video of the simulation of this drone that consider to simulating on the space of a city. What is the future improvement of this project? Well, the future improvement is uses in different advanced adaptive and robust control that determine the stabilization of the under different payloads or more payloads and wind variations. Additional to this is the real-time path planning, which use the leader's land to map in different areas. Other implement of this project is for physical prototype, for example, to use the Holy Pro X500 for field testing and simulate. Well, this is all the presentation. Thank you.